In this exercise, we'll discuss a transient species balance for this mixer in front of us, and then we'll also discuss the 12 design steps that we've discussed for dynamic modeling. First, let's write start a species balance for species A, we'll call it. And so we want to know the change, so let me change the tool, change in moles of A over change in time. And we'll start with a species balance. We can then move on to a concentration balance or a mass balance if needed. But we'll start with that. And very simply, if we think of accumulation, here we have our accumulation term, and since we're just doing a mixture, no sort of reaction, we won't have any generation or consumption, so it should just be in minus out. So we have two streams coming in, and they're labeled 1 and 2. So let's just write this very briefly as N1 plus N2 minus N dot 3. So the dot here just makes it so that it's a differential term. It's a flow rate. So dN, the change in moles of A within the reactor per time, is equal to the flows in. I'll go ahead and I'll write that, minus the flow out. N dot 1 is really equal to CA1 times Q1, where Q we're assuming is the volumetric flow rate. Same thing with N2 and N3. I'll just go ahead and write a generalized term. N dot I is equal to CA I Q I. It's a Q, not an A. So then we can make a concentration balance just by separating out the terms in our balance. So we'll go ahead and we'll write dCA times V, we have a constant here, dt, is equal to CA1 Q1 plus CA2 Q2 minus CA3 Q3. Now one assumption we'll want to make right here, and I'll go ahead and I'll just write it off to the side that way we remember it. And it's a very handy one we use often with mixtures and CSTRs, is we're going to assume well mixed. And when we make that assumption, a portion down here is going to have the same distribution of chemicals as a portion up here, or a portion up here, or a portion up here. And that means that the stream coming out has the same concentration as whatever is happening inside the tank itself. Now we're going to use the chain rule. We have two differentials here. We have the CA, we have the V. We need to take the chain rule of that in order for it to work right. I'll go ahead and just write that. It's going to be the first one to be constant, and then dCA3 dt plus, we're going to take the second one to be assumed constant, CA3 dV dt is equal to, I'll go ahead and I'll just lasso this portion. It's going to be the same. With this equation in place, if we assume constant volume, we can eliminate this term. Here we'll write the equation now with a constant volume. We'll go ahead and we'll take this term, we'll put it underneath. So we get the differential of concentration out per time is equal to this relation down below. If we don't have constant volume, then we will add a mass balance instead. And we'll do that, I'll just write a separate arrow. We'll know that change in mass of the system, of the tank, per time is equal to the mass in minus the mass out. mass should be equal to density times total volume. And similarly, mass flow rate, or m dot, should be equal to the density times the volumetric flow rate. We can write the differential volume now for our total balance with respect to the mass balance by using these densities and mass flow rates, volume flow rates. Finally, if we assume density is constant, then our differential volume will be only based on the volumetric flow rates. Let's discuss the 12 steps in dynamic modeling. So we already have our objective. Our objective was to find a balance that included both volume and concentration out. Next, we wanted a schematic diagram, and then we want to list all assumptions. We have our schematic. We do already have all of our parameters already labeled on it. So we'll go ahead and we'll talk about the assumptions we made. And this depends greatly on what material we have going on, and that's why, as engineers, it's so important to understand the physics, the principles of what's actually going on in our system, so we can understand what assumptions we can make. The first one, and the one we'll probably make most often, is assuming that it's well mixed. We also discussed assumptions such as constant volume and constant density and what those effects may be. Next, we'll determine any spatial dependence. In this, in a CSTR, I'll just go ahead and draw one. Especially if we assume that it's well mixed, then there shouldn't be any spatial dependence. So we have a simple. Next, we have our balances. That's what we just worked on. We had this mass balance, and we don't have any sort of thermodynamic or stoichiometric relations, because this is just a mixer. That's all that's going on. So a mass balance or species balance is all that we really have going on. If we were to control this system, we have 2 inputs and 1 output. The main thing we would probably control is one or both of the inlet values, and probably the flow rate of one of those or both streams. Manipulative values could be, for example, how well it's mixed, or it could be the concentration. Outputs would be the volume right here and the concentration here. The volume inside the tank and the concentration out. These would be states, since we're not actually controlling it in this problem, but they could be controlled variables if we did adjust something to control those. Finally, we'd want to simulate a dynamic and steady state system to make sure that our system works well, but that's not necessary for this problem. So instead, here's our final balance, our simplified balance with our assumption. Go ahead and let me know if there's any questions you have, and you can check out the rest of this course or any other links you'd like in the links down below.